So now we have collisions at angles. And we have to remember that momentum is going to be conserved, and momentum is going to be conserved in each direction. So it's going to be conserved in the x direction, and it's going to be conserved in the y direction. So we have a T-bone example. Two cars are driving towards an intersection. One's traveling from the east, or traveling to the east, I should say, and the other is traveling north. And we want to figure out what speed and direction they move after the collision when they collide inelastically. So they're going to get stuck together completely. So the first thing, we still want to draw a before and after picture. We also want to write a conservation of momentum equation. This is going to look a little different from what it did before, but it's still a conservation of momentum equation. So we have our two cars. This is our before picture. And I made the yellow car a little smaller because it only has a mass of 800 kilograms. It's maybe a smart car. And the larger car has a mass of 2,000 kilograms, so it's more like a very large American-sized pickup truck. The after picture has them both combined, and I want you to think, which way are they going to be going? Will they go directly east? Will they go directly north? Or will they go somewhere in between? And if they go somewhere in between, will they be going more north? Or will they be going more east? So the first thing we need to do, we've got our before and after picture. Now we can write a conservation of momentum equation. Let me show you what that looks like. And it's going to look a little strange. So we have momentum of car 1, and I'm going to put an arrow on top to make sure we know that it's a vector, plus the momentum of car 2 with another arrow equals the total momentum. So this is the momentum of car 1, momentum of car 2, and then they are going to go off at an angle. So that's our total momentum. Now, with that equation, I don't want you thinking that I'm adding them algebraically. I'm not taking the magnitude of the first car's momentum and the magnitude of the second car's momentum and just adding them like I would add 3 plus 5. This notation, especially with the arrows on top, actually means what I'm doing if I had a vector going this way, and if I had another vector going that way, then my resultant vector would look like that. So it's adding them head to tail. When I put the arrows on top of the vectors, it means I'm adding them head to tail, and I'm adding them like vectors. I'm not adding them in the way you would in a straight up math class. So now we need to do a little bit of calculation. Also, remember that the momentum before the collision should still be there after the collision. So whatever the momentum of the first car was, it's actually still going to be there after the collision. And whatever the momentum of the truck is, it will also be there after the collision. Let's calculate these. So the momentum of car 1, the small car, should be 18 times 800, the mass of the car times its velocity. So this is 14,400 kilograms times meters per second. And for the second car, we take 2,000 kilograms times 13 meters per second. So this is 26,000 kilograms times meters per second. Momentum is conserved. So the momentum in the east-west direction will still be there after the collision. So this side is 14,400. And the other side is also 26,000 kilograms times meters per second. Are you starting to see where we're going with this? We've got two sides of a right triangle, so we need that side. So what do we do now? A squared plus b squared equals c squared. So plus b squared equals c squared. So we take 14,400 squared plus 26,000 squared equals our hypotenuse squared. Those are some very big numbers, so we have to square them, add them together, and then we also need to make sure we write the square root, take the square root of both sides. Because those numbers are quite long, I'm not going to write them out, but our total momentum winds up being 29,721 kilograms times meters per second. But we're not done yet. We still haven't answered our question. We're looking for the speed and the direction that they're moving at. So let me erase this slide and we'll keep going. So we just solved for that total momentum. (29,721 kilograms times meters per second). I'm not going to round until I get to my last step to make sure I don't have any rounding errors. Momentum is mass times velocity. We have our total momentum. What mass are we going to use? We're going to use the combined mass of both of the cars. So this is 2,800 times the velocity. So our velocity at the end of this should be 10 meters per second. Now, I want you to know, we just drew a lot of triangles, and a lot of times when we draw triangles, we just need to solve. Be careful when you're drawing your triangles to make sure that your triangles are made out of momenta. Make sure that this side and this side are your calculated momentum. The only thing that is conserved before and after the collision is the momentum. If you try to solve this using a triangle made out of the velocities, you're going to get a very, very different answer. If you try to do it using just 13 meters per second and 18 meters per second, you'll get a velocity of 22.2 meters per second, which is very different from our correct answer. So make sure that you're calculating those velocities. This one is the one we've been waiting for. So in this case, we have a hockey puck, and it hits another stationary hockey puck with a similar mass. And then the two hockey pucks travel in different directions from each other. They're not going in straight lines. This one, we've got a little bit of hint before we get started. So the first hint I've got for you is that the angles between these two objects will add up to be 90 degrees. And this only works if two things happen. First, one of the objects must be at rest or stationary. And secondly, the masses of the two objects must be the same. We're still going to draw a before and after picture, and we're going to write the conservation of the momentum equations. And for this one, I've got two ways to solve it. The one way is long and algebraic. It's got a lot of math in it. And the other one, we get to be sneaky physicists, and it's a shortcut. Okay, so this, I've already got it all set up. It still has the same information that we were given before. We have one object that was 0.2 kilograms. It had a velocity of 50 meters per second, and it hits another very similar object with a mass of 0.2 kilograms. And then they bounce off of each other elastically. One goes off at an angle of 37 degrees, and the other goes at an angle this way. I've already written in that this is going to be 53 degrees because we know that they have the same mass and one of them is stationary, so the angle between them should add up to be 90 degrees. So this is the long way to solve it. We're going to solve it algebraically. So first thing we need to do is set up a conservation equation for both the x and the y axis. In the x-axis, we have momentum before and momentum after, and those momentum should add to the momentum in the x direction on this side should be the same as the momentum in the x direction on this side. Before the collision, there is no y momentum, so we know that the y momentum going this way and the y momentum this way should cancel each other out and be 0. So let's write out our equations. So I'm going to start with y. So in the y direction, we know that before we have 0 momentum. And afterwards, we know we have the momentum of object 1 in the y direction. And I'm going to put a prime here so that we know it's after. And we have this is going upwards, so it's positive, and this one is going downwards, so it's negative. So we are going to write minus P2 in the y direction after the collision. So that's one equation we have. The other before and after conservation equation we have is in the x direction. So in the x direction, we have some momentum before. We have P1 as our momentum, and that's going to equal P1 in the x direction after the collision plus P2 in the x direction after the collision. They're both going in the same direction in the positive x direction, so they're both added together. Now I am going to keep the numbers out of our equations for a little bit, just to make them a little easier to manipulate, in my opinion. So that's why I called theta 37 degrees and 53 degrees, I'm calling it beta. So over here, these are just the components, so we named them as their components. But what we're more interested in is their velocity and their momentum in that direction. So we really want to know this. So let's rewrite that in terms of our overall momentum for each particle after the collision. So this, our y velocity, is going to be from the sine of that angle. So we have P1 prime times sine of theta minus P2 prime sine of beta. And those are still going to be equal to 0. In the x direction, same thing. And if you want to work just the y equations and then just the x equations, that's okay. I'm working kind of both at the same time until we get to a certain point, and you'll see when I switch. P1 equals P1 prime. These are the x directions, so it's cosine theta plus P2 prime cosine beta. Okay. Next step, I like for my next step, I like to put everything in terms of mass and velocity. And you'll see why in a second. So take a look. We know 0 equals m, and we know m1 is the same as m2. So I'm not going to write m1 and m2. I'm just going to write m. So we have m v1 prime sine of theta minus m v2 prime sine beta. Same thing over here. We have m v1 equals m v1 prime cosine theta plus m v2 prime cosine beta. Now look at all of these equations, or both of these equations. M exists in every of these terms. That means we can cancel it on all of those terms. We can divide by m on both sides of this equation, and we can divide by m on both sides of this equation. So the mass doesn't really matter in this situation. So we would get 0 equals v1 prime times the sine of theta minus v2 prime sine of beta. Same thing over here. We divide by m on both sides, so we get v1 equals v1 prime cosine theta plus v2 prime cosine beta. So that just means a little less math that we have to do later on. Now, what things here do we know and what things don't we know? Because we're about to the point where we probably need to start plugging in numbers. We know theta and we know beta. We were given theta, and because these objects have the same mass and one was at rest, we can easily figure out beta. So those we don't need to worry about. We know v1. v1 was given to us as well. So the things here that we don't know are v1 prime and v2 prime. So we have two unknowns. And as math teachers like to say, if we have we need two equations to solve for two unknowns. And we have two equations. We have this equation and this equation. That also means that we will have to do a lot of substituting and a decent amount of algebra. One thing you could do is, if you realize that these are 90-degree angles and complementary angles have some nice properties when it comes to sine and cosine, you could do some substituting and rearranging there. I'm not going to do that one because I think that's a little bit too much geometry. I'm just going to stick to the algebra for this one. Okay, so we have, I'm going to add one of these terms to the other side. So v2 prime sine beta equals v1 prime sine theta. And over here, I'm just going to leave this equation alone for a bit. And now I'm going to plug in some numbers over here. So we know, before I plug in some numbers, I'm going to divide by sine of beta on both sides. You don't have to. If you want to start plugging in numbers now, that's perfectly fine. Sine theta divided by sine beta. So now I'm going to start plugging in my numbers. v1 prime is going to be sine of theta is 0.602. Try to keep the numbers as long as you can before you start rounding. So if you want to keep it long, that's perfectly fine. I've got it in my calculator. So I'm just going to write a little 3 decimals. Okay. Let's see. Now we can divide on both sides, so I'm going to bring this over here. When you start moving around your paper, doing your equations, be sure your teacher can follow you. You can always write a little arrow. And also make sure you bring down both sides of your equation all the way down when you're solving long equations. So this is 0.754 over there. And we've come to the end of this part that we can work. Now we have to plug it into over here. So, and I think I'm going to switch papers. I'm going to move this up a little bit. So, we had from the other paper, let me rewrite it, we left V1 as V1 prime cosine theta, and we plus V2 prime cosine beta. And we just got to the point where V2 prime equals V1 prime times 0.754. So over here, we know V1. V1 is 50. We don't know what V1 prime is. We know what cosine theta is. Cosine theta is 0.799 plus V2, and we know what V2 is, at least in terms of V1. So now we have V1 times 0.754 times cosine of beta. So this is 0.602. So we have 50 equals V1 prime times 0.799 plus, multiply these together, V1 prime times 0.481. We can add these together because they're like terms. They both have V1 in it. So this is 1.279. Remember, I am keeping a couple extra decimals in my calculator. That's why these numbers don't quite match up. Times V1 prime is 50. So V1 prime is going to be divide by 1.279 on both sides. So V1 prime is 39.1 meters per second. And V2 prime, take that number, plug it back in over here. .5 meters per second. So that's how fast our two objects are going this way and this way. So P1, object 1, is going 39 meters per second this way, and object 2 is going 29.5 meters per second this way. Now, so that was the end of the long way. Let me show you the short way now. So I've got our same setup. We have P1. This is the momentum before the collision. This is the momentum after the collision. But notice I still have P1 over here because we know momentum should be conserved before and after the collision. I also have a vector addition equation up here. So this is saying that if we have P1 and add it to P2, then we should have a nice complete triangle with P1, our initial P1, as our resultant. So how can we get this equation to match our picture over here? And what we're going to do first is we're going to remember some of our properties of vectors. We're going to remember that we can slide our vector any which way we want. So long as we don't turn it and twist it, we can slide it this way. So that's what we're going to do. So we should be able to slide this vector over to over here. Now, one thing when you're doing this at home, I've already measured out these angles. So I measured this angle here, and I was very careful to make it 37 degrees. 37 degrees. And I measured this angle, and I made sure that it was also 53 degrees. So this one's 53 degrees. Now, one thing I want you to think of while we're drawing this, if I have, let's say I have my two lines going here, and those are parallel to each other, if I have an angle here, what other angles are the same? From geometry, we know that angles that make a nice big Z in parallel lines, so if we have two parallel lines and they're cut through by another line, these angles inside the Z are actually going to be the same angle. So if we're trying to get this angle, or sorry, this momentum vector, and slide it up to here, this angle is also going to be beta. So we can take our protractor and measure it carefully. The measuring carefully comes in handy for another step. So it's going to line up right there. That's 53 degrees. So from here to here, that's going to be the same momentum. And the reason, like I said, we can do this is because momentum is a vector. We can add our vectors in any order we choose. We add them head to tail, and we can slide them or shift them so long as we're not changing the angle. What does this look like? We know this angle here is 90 degrees. This is a triangle. We know theta and beta is 90 degrees, and we know triangles have to add up to be 180 degrees. So this angle is also 90 degrees. So this gets to be a little exciting in my opinion. But of course, I love physics. I'm going to turn this just to make it a little easier to see because our triangle is a little upside down. Take a look at this. We have a right triangle. Our momentum after the collision are the legs of the triangle, and the momentum before the collision is the hypotenuse of the triangle. So in this case, because our objects had the same mass and because one of them was standing still, we get this nice right triangle. And rather than solving all of the algebra that we had to do before to find the velocities and the momentum, all we have to do now is use sine and cosine and the hypotenuse to find these angles. So we have P1 prime is going to be P1, our momentum before the collision, times the cosine of the angle that our object makes, that our first object makes from its original path. And P2 prime is going to be P1, our initial momentum. I'm going to use cosine again, times the cosine of the angle that it makes from the first object's original path. That's so much shorter. Okay, so let's go ahead and solve it. So P1 prime is going to be P1 cosine theta. I always like to rewrite my equation just to make sure that I get it right and so that I know it really well. If your teacher makes you memorize the equations, make sure whenever you're solving your homework, that is the first thing you do. And even if the teacher doesn't make you memorize the equations, make sure you write that equation every time so that you don't make a mistake. So I'm going to calculate the momentum over here. The mass is 0.2. The velocity initially was 50 meters per second. So this momentum is 10 kilograms times meters per second. So over here we have 10 cosine 37. So this momentum, momentum prime is 7.99 meters per kilograms times meters per second. That's P1 prime. P2 prime is P1 still, because that's our hypotenuse, cosine beta. So this will be still 10 cosine of 53 degrees so this is 6.02 kilograms times meters per second. Now that's not our final answer, but all we have to do is divide by the mass for both of these, and we should have the same velocity. Now remember our velocity from before that we calculated before. We found V1 was 39.1 meters per second, and V2 prime is 29.5 meters per second. So divide by the mass on both sides. So this is 30.1 meters per second with this calculation. And this one is 39.9 meters per second. We are not all that far off from our initial calculations, but which one do I trust more? Personally, I trust these more. We did not have to do as much calculation. We didn't do as much rounding. So I think these two will be a lot closer to the true value. And another trick, bonus shortcut. If you were very careful and used a protractor and measured everything out. So this just so happens to have a momentum of 10 kilograms times meters per second. So I measured this side, when I drew it, to be 10. And then I knew that the angle here was 37 degrees. So I made my line as long as I wanted, 37 degrees out. And you just draw the line as far as you can. And then on this side, you use 53 degrees, and you also draw a line 53 degrees until these two lines meet. And then, if you're sneaky, you can measure it. This momentum, it's a little hard to see, but this momentum is very nearly 8. What did we calculate our momentum to be for P1 prime? Very nearly 8. What's the momentum for P2 prime? 6. And we're measuring very nearly 6. Bonus shortcut for the cunning. And that is the end of how you calculate these problems, both the long way and the short way and the super short way with your protractor. So remember, that shortcut only works because we could tell the angles between the two. So some of those calculations, we assumed we knew both of the angles, and we could assume we knew both of the angles because we knew that they had to add up to be 90 degrees. The only way we know they add up to be 90 degrees is when the masses are the same and one of the objects was stationary. There are other videos on YouTube that you can find that show the proof of that. They're a little bit long, but feel free to find them. I'll put some links in the comments section so that you can find them. So the key ideas from this video is that momentum is a vector, which means all of the properties of vectors apply. So we can add it head to tail, we can add it in any order, we can shift it around, and we can break it into components, all of which we can make our problem solving easier. And momentum is conserved, which means momentum is conserved in each direction. So if we have momentum in the x direction before the collision, we will have the same momentum in the x direction after a collision. Same thing with the y direction. Hope that was helpful. You can find me at Hey Mrs. Physics on Twitter, and I hope you join me in being part of a culture of discovery and lifelong learning. Feel free to subscribe so you get notifications, and also follow me on Twitter so you can contact me and ask questions. Hope to see you soon.